Example 4. A model airplane flies horizontally at 22 meters per second. Cool. Sam, what does A want me to find?
Kinetic energy.
How do I calculate kinetic energy?
KE initial plus...
Just straight kinetic energy. Don't worry about conservation of energy. It's just going to be KE equals a half.
mv squared.
Yep. Okay. It's going to be 0.5 times 2 times 22. Don't forget the squared. How many joules of kinetic energy does it have? It has 0.5 times 2. Mr. Do it clear. 0.5 times 2. I guess I could have skipped that because half of 2 is 1. But, okay. Times 22 squared. 22 squared, Mr. Dueck. Do you get 484 joules? That's how much kinetic energy of motion it has. The plane is up here, and it goes into a dive. When it goes into a dive, it's going to lose height. It's going to lose potential energy. Is that okay, Rowan?
Yes.
So what does B, Rowan, want me to find? How much what?
Power.
Read carefully. It's also in your notes in front of you, but I'm glad you're squinting at the board there. How much?
Oh, potential energy.
Good. And Logan, how do I find potential energy? Because you whispered it to Rowan. It's on your green sheet. Find it. By the way, if you stop looking at your notes for the formulas, get in the habit of looking at the green sheet. Train your eyes subconsciously where to look. It works. How do we find potential energy? So PE equals? Yes. What's the mass? 2. What's G? 9.8. The height is 40.5. Now, this is an energy loss because we're diving down. Our height is decreasing. So that's why I said how much it lost. What do you get when you go 2 times 9.8 times 40.5? Y'all get 793.8? That energy had to go somewhere. It can't just vanish. Where did the energy go? What happens to an airplane when it dives down? It turned into kinetic. And this is why when a plane dives down, it speeds up. Okay? So C, how much kinetic energy did the plane gain? The plane gained 793.8 joules. Now we're ignoring air resistance. In real life, it would have lost a little bit of energy to air resistance and to sound, but we're in our magic physics world trying to make the numbers work out nice, Rowan, so we're okay. This is what the law of conservation of energy says. It says energy can't vanish. So what's its new kinetic energy? Part D. Well, kinetic energy, you know what? I'm going to call it final instead of the word new. Is that okay, Savannah? Because that's often what we've done for the later. Savannah, how much kinetic energy did it start with? How much did it just gain? I think I'm going to add them together. And here's the nice thing. In real life, Savannah, the path that the plane took, if you look up, it would be all curvy and yucky and slanty, but because energy is a scalar, it doesn't care about that curvy path that you took diving down to get there. It just cares about where you started and where you ended. So it's going to be 484 plus 793.8. It now has 1,277.8 joules of energy. Which means I can tell you how fast it's going now. Jabber, what does E want me to find? That's a typo. Can you all cross out the word velocity and replace it with the word speed? Because energy is a scalar. It doesn't give us a vector answer, and I'll fix that in my original. Well, what did I find in part D? Let's write down the equation for kinetic energy. A half mv squared. Jabber, do I know the kinetic energy? Do I know the mass? Well, then I can find V. How would I get the V by itself? Good. So you're saying the kinetic energy would drop down like a domino, divide the M. How do I deal with that 1/2? You can either go times by 2, or you can divide by 0.5, same difference. Now, that would give me, Jabber, a V squared. Can you take it home? Yes. Is that okay? We're going to be doing that one there quite often, because one of the questions I guarantee I'll ask you is finding how fast a roller coaster goes. In fact, I'm willing to bet on the next page or two, I think I have a couple of roller coaster questions. So it's going to be 2 times 1,277.8 divided by, what was the mass? Was it also 2? Okay. And I got 35.7, 36 meters per second. Yeah? How fast was it going originally up there? What was its speed? Sorry, 22, it dove down and sped up. And again, most of you are, well, I kind of figured that out from watching movies or being in airplanes. When they dive down, they speed up. But again, Blake, there's the why. You don't need to write this next bit down, but before you turn the page, here's what we really said. We said the amount of kinetic energy that we started with and the amount of potential energy that we started with had to equal the amount of kinetic energy that we finished with and the amount of potential energy that we finished with, except I was a bit sneaky, Kenley. I didn't tell you how much we started with for potential energy. I just told you how much we gained over here. Oh, roller coasters. Let's ride a roller coaster. Suppose the 320 kilogram roller coaster below is at rest. You know what? I'd probably mentally underline the word at rest, because what's VI then? What's my initial kinetic energy then? Also 0. Let's come back to that. At the top of the first hill, it's given a very gentle push and starts to roll. Evan, what's A want me to find? So we're going to use, well, here's what I would say. Can you imagine the roller coaster? Is there a change in height? Is there a change in speed? Is there a yucky, curvy path? That's a job for conservation of energy. Okay? So I'm going to let this be initial and this be final. And Evan, I know you were away. Antonio, can you read to me the law of conservation of energy equation? The short version is the amount of energy you start with has to equal the amount of energy you finish with. Now, remember, potential energy is mgh. Kinetic energy is a half mv squared. So before I go diving in, I always ask, are any of these 0? Actually, Evan, you already told me one of these is 0. What did you tell me was 0? The initial? Because initial V is 0, so you can cross that out. Are any of these other 3 0? If you're on the ground? Because your height is 0. And so this equation modifies into mgh initial equals a half mv final squared. Sam, how many terms are there?
2.
Is there an m in this term?
Yep.
Is there an m in this term? Is there an m in everything?
Yeah.
You know what that means? What?
Talk about?
Sam, have you been on a roller coaster before?
Yeah.
Before you went on the roller coaster, did they make you stand on a scale? Did they have to balance everybody out? Did they have to make sure that heavy people sat next to light people? Did they have to make sure that they spread the little kids out? You know why? Because mass cancels. Or will an empty roller coaster make it all the way through the track the same way a full roller coaster will? Yes, I've watched it happen when I'm at Playland before opening, when they're testing the rides out. They send an empty car through as a test. And that's why when you got on the roller coaster, they didn't make you stand on a scale. Mass cancels. Now, in real life, there's also a little bit of energy loss due to friction, but as long as we grease the coaster down pretty good, the mass almost cancels, enough that we're not worried about it. What are we trying to find, folks? Evan, what are we trying to find? Which is which of these? V. I don't want the. I want to get rid of the squared. First of all, how would I move this 1 over? Well, technically I'd divide it over because it's on the top. Will dividing by 1 change anything? How do I move this 2 over? Well, this 2 is on the bottom on the right, so where will I put it on the left? So if you want to, you can cross out this 2 and tuck a 2 right there. And we've taken care of the 1. That leaves us with a VF squared. Evan, how to get rid of a squared? Just for neatness, so here's what you're saying. VF is going to be the square root of 2GHI. I'm willing to bet that roller coaster designers have that equation memorized because they use it all the time. This is how fast you'll be going at the bottom of the first hill. If you're not sure if the mass cancels, by the way, Sam, you can't put the 320s in. You'll get the same answer as us. But I did want to point out, maybe you've never thought about it, but yeah, when you get on a coaster, there's a reason why you don't have to step on a scale, why we don't have to spread everybody out very, very, very carefully. It's because the M cancels here. It's going to be the square root of 2 times 9.8. What was the initial height? Oh, 90. This work out evenly? This might work out evenly. Does it? What'd you get? That's meters per second. Could you convert that to kilometers per hour? I want to know if this is a coaster worth going on. Huh? Oh, I'm going on this. This is serious. This is world class. Okay? In real life, you wouldn't quite get the 42. You'd lose some to air resistance, some energy to bumping off air molecules, and you'd lose some energy to heat. You'd probably be hitting 35 or 36. But even that, I'm going on this. This is, my eyes are going to water. I'm going to be pretty screaming. This is going to be a great, intense ride. Okay? B. How fast will it be going here? You know what I'm going to do? Antonio, I'm still going to have initial B here, but for part B, scribble, 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 I'll let that be final. Is there a change in height? Is there a change in speed? Is there a yucky, curvy path? You want a scalar approach, conservation of energy. This is a job for conservation of energy. So, KE initial plus PE initial equals KE final plus PE final. I think on your formula sheet, I wrote potential energy first. I think when I write it out from memory, I write kinetic energy first, but it's initial plus initial equals final plus final. That's the formula. That's the approach. All of the energy you start with equals all of the energy you finish with. Are any of these 0? Yeah? I'm starting here. The reason I'm not starting here is if I start here, I'm using this answer, and if I got this answer wrong, that means I'm going to get this answer. I don't have a problem, honestly, with starting there, but I figure I'll start here with what they gave me. Which means I'm starting at rest. That one's 0. Sadly, nothing else is. So my next line is going to be MGH initial equals a half MV final squared plus MGH final. Adam, what's this question wanting me to find? Hey, Adam, how many terms are there here? Is there an M in this term? Is there an M in this term? Is there an M in this term? Have you been on a roller coaster before? Before you got on, did they make you stand on a scale? Did they have to weigh you and carefully spread out all the masses? Do you know why? And again, if you're not sure, you don't have to cancel out the masses. If you're not sure, you'll get the same answer. But am I going to take the nice, lazy shortcut? Yes. Now what? I need to take care of this thing and this thing, and I'm going to do reverse bed mass. So I'm going to take care of any plussing or minusing first. What's going to drop down like a domino? Yep. That guy. Clunk. Keep going at him. So minus it over, because it's a plus sign right there, so I'll minus it. And then in my mind, I imagine I have a 0.5 V final squared. Keep going. So you can, if you want to, go times by 2 times by 2. Or you can divide the whole thing by 0.5. Either one of those, Jagger does exactly the same thing. So I'm going to end up with, running out of room here, V final being the square root of 2 times 9.8 times 90 minus 2 times 9.8 times 50. Oh, I think this works out evenly too, quite amazingly. Now, how will you type that into your calculator? You'll go 2 times 9.8 times 90 minus 2 times 9.8 times 50 equals square root answer button. You get 28? Those of you that have the newer calculators with the multi-level displays, you can probably type this inside a square root, and so you don't need to do the way I did. 28 meters per second at the top of the second hill. That's still pretty good. 28 meters per second, that's around 30 times 3 points. That's around 100 kilometers per hour at the top of the second hill. I'm in. That's good. Probably you're going fast enough at the top of the second hill that you feel like you're getting pushed up against your shoulder restraints. You feel like you're getting pushed out, and that's a feeling that really adds to the terror. We're all used to feeling heavier. We're not that used to feeling lighter when the normal force decreases. And so you get some good screams at the bottom, right around here on the free fall. Here at the very bottom, you'd feel heavier. But here at the top here, you'd feel lighter again. So this is a good coaster. Suppose there's a third hill. I didn't show it. And at the top of that, the roller coaster has a speed of 12 meters per second. How high is the third hill? So you'll need to imagine kind of a third one there. You could draw it in, I guess, if you want to. In my mind, then, that's going to be final. Is there a change in height? Is there a change in speed? Is there a yucky, curvy path? Conservation of energy is going to work really well. KE initial plus PE initial equals KE final plus PE final. Or PE initial plus KE initial equals PE final plus KE final. Initial plus initial equals final plus final. Is that okay, Rowan? Are any of these 0? Still starting at rest? Are we ever on the ground? We're starting on the top of a big hill. We're ending on the top of a smaller hill. Not on the ground. MGH initial equals a half MV final squared plus MGH final. Kenzie, what am I trying to find this? Oh, sorry. Kenzie, how many terms are there? Is there an M in everything? Have you gone on a roller coaster before? before you got on? Did they make you stand on a scale and weigh you? They did not. Why? Because if we ignore friction, or in real life, if we grease them down, which we do, and we make them pretty aerodynamic, which we do, you can pretty much ignore the mass. In our magic physics world, you can completely ignore the mass. In real life, it's negligible, which means it still shows up, but not enough to make an empty or full car not make it through. Because that would be the big danger, is it didn't make it up one of the hills and just went back and forth, and came to a rest at the bottom of one of the hills. That's a problem. What are we trying to find? Yes? Talk to me. What's going to drop down like a domino? Or better yet, what's going to drop down like a roller coaster going down a hill? GH initial. And then keep going? Yeah, I got that part, but I want to get the H by itself. So now what? What's this G doing to the H? So I will divide. What's this 0.5 or half V squared doing to the H? There's a times there? Ah, reverse BEDMAS. Take care of the adding. How? What's the opposite of adding? Minus 0.5 VF squared. And then just use your imagination. Mackenzie, don't write this down. Don't write this down. But in my mind, I imagine it equals G times H final. How would I get the H final by itself? So now I'm going to do this, actually writing this down, divide the G. And do you mind? I'm going to put the H final on that side because that's where we're used to seeing this stuff by itself. Another question that you might want to do is find H initial. How high do I need to build the first hill? Right? You behaving yourselves? Because I'm catching you. 9.8 times 90 minus 0.5 times 12 squared all over 9.8. This one is complicated enough. I would strongly encourage all of you to try typing this in. Mackenzie, is this a fraction? Is there more than one thing on the top? I'm putting brackets around the top. Although I only got one thing on the bottom, so I don't need brackets around the bottom, but I would encourage all of you to try typing this in. 9.8 times 20 minus 0.5 times 12 squared. Close off the top, divided by 9.8 times 90. Why did I write times 20? Because I can't read my own writing, apparently. I read that as a 2. Thank you. So if we want on the third hill the coaster to have a speed of 12 meters per second, how high do we need to design the hill? You get 82.6. Still pretty high. If the original biggest hill was 90, you've still got a fair bit of kinetic energy. Yeah, okay. You're going almost 83 meters high. You're making it almost all the way back to the top. In fact, 82.7 if I round off properly. You know what? I'm going to go 83 meters. I'll go to 2 sig figs just because. Is that okay? Just flexing because you felt like you needed to? There's going to be a roller coaster question on your energy test. In fact, there's going to be 2 or 3 roller coaster questions on your energy test because it's roller coasters. Is this the last one? I think. Yes, it is. Good. Okay. Roller coaster travels as shown below. At point A, it's moving at 12 meters per second. So this time it's not starting at rest, which is a bit more realistic because when you come over that first hill, you do have some speed from the rope. That's gravity. We looked at that, but we'll come back to it. Cool. Jagger, what's A want me to find? Is there a change in height? Is there a change in speed? Is there a yucky curvy path? I'm going to solve this with conservation of energy. I think I'll let initial be right here, and I think I'll let final be right there. I'm going to freeze the screen Try this one on your own. Use the law of conservation of energy. I'll unfreeze the screen every so often if you get stuck along the way. This is going to be pretty tricky. The reason this one is tricky is I think only your final potential energy is 0. In fact, if you want to, I'm going to show you a good trick. Look up. I think many of you in Math 11 just finished a unit on equation solving rational or fractional equations. First of all, Sam, do the m's cancel or not? Yeah. Okay, do that. Sam, what am I trying to find? Which is which variable in this equation?
V.
Sorry?
V.
Which V? Because there's 2 of them. VF. Okay. What am I trying to find?
VF.
What am I trying to find?
VF.
See that 1/2? See that 1/2? If you want to, you can clear fractions by going like this. Times by 2, times by 2, times by 2. Now you have to multiply the non-fraction term by 2 as well because you're multiplying everything by a common denominator. You learned this not very long ago in Math 11, I think in Mr. Gerard's class. If you do that, 2 times 1/2 is 1. 2 times 1/2 is 1. And you end up with this equation. VI squared plus 2GHI. And then, Sam, do you mind? I'm going to put the VF squared right there. Is that okay?
Yeah.
Write that down. And then put your pencil down for a second. Write that down, and then put your pencil down and look up. Got it? Do you know what we've just derived without realizing it? Look up, look up, look up. VF squared equals VI squared plus 2AD, because isn't that an acceleration, and isn't that in meters? It pops out of conservation of energy on its own very nicely. I think at the beginning of the year, I told you that I would derive that equation later because it's going to pop out really nicely on its own from energy. I can get there from kinematics, and I've done that. And I'll do it in Physics 12 just because I'm a nerd, but I did promise way back, I think in middle of October or November, I'll show you where that came from. It pops out right there. Is that all right?
Yeah.
What am I trying to find, Sam?
Yeah.
Have I got the VF by itself?
Yeah.
No.
Oh, V squared.
So everybody pick up your pencils. Square root. So it's going to be the square root of, what was VI? Was it 12? Squared plus 2 times 9.8 times 18. This might work out nice. 12 squared plus 2 times 9.8 times 18. I take that back. Maybe not. Yeah. You get 22.3 meters per second. And now we can be, Riley, a little more accurate. Supposing I went to the bottom of that roller coaster with my radar gun. I do have a radar gun. And I clocked it coming by not at 22.3 meters per second, but at 15 meters per second. Does that mean that I violated the law of conservation of energy? No, it means the energy went somewhere else. Heat. So B says, if the coaster is only traveling 15 meters per second at point B, how much energy was lost to heat? We have to modify our conservation of energy equation. It still starts out as potential initial and kinetic initial equals potential final plus kinetic final. It still starts out as initial plus initial equals final plus final. But Savannah, if the numbers don't balance, it's because whatever's left over went into heat. And I'll just write out the word heat. And I'll do it in red so it looks heat-ish. Looks hot. Are any of these 0? Still that guy. Because we are on the ground, yes? Okay. Jackson, what's this question asking me to find?
How much energy was lost to heat?
Wants me to find that. Okay, how would I get that by itself? How will I move the KE final over?
Copy.
Yep. Yet another equation, don't memorize it. So I guess the whole left side drops down. Potential initial plus kinetic initial minus kinetic final. And do you mind, Jackson? I'm going to put the equals heat over on this side by itself. Alrighty. Heat is going to be potential mgh initial plus kinetic a half mv initial squared minus a half mv final squared. Sam, how many terms are there here?
4.
Is there an m in everything here?
No.
So does the mass cancel this time? So in real life, if you lose a lot of energy due to friction, you might not make it through the track. But as long as we grease them down, we're good. Okay? What was the mass? I've scrolled down. Did they tell me? I hope. Sorry? 245? Times 9.8 times, was the initial height 18? Plus 0.5 times 245 times 12 squared. I think that was the initial V. Minus 0.5 times 245 times, I'm not going to use 22.3, Blake. They said actually we're only going 15 meters per second. Don't forget the squared. How much energy do we lose to heat? I can type this in, I think, in one line. 245 times 9.8 times 18 plus a half m v squared minus a half m v squared. We should get a positive answer because there was some energy left over for heat because this thing slowed down. I got 33,295.5. Someone else? I'll call it 33,300, I think. I'll round off to 3 sig figs. Units for heat. Well, heat's a form of energy, so really units for energy. I heard it. Joules. You want to make that smaller? Grease your coaster down. And also make it more aerodynamic, and you'll lose less to air resistance as well. And there's a reason why most roller coasters all look alike. They look bullet-shaped because we don't want to waste energy for aerodynamic. And they all have these metal wheels that roll and spin really nicely and are greased down pretty well. They roll pretty smooth. That's the law of conservation of energy. What's your homework? Number 1. Little note, ME is mechanical energy, and it's just the potential plus the kinetic. We can do number 1 together. What's our potential energy right now if we're on the ground? What's the kinetic energy? A half mv squared. What's the total energy? 0 plus whatever a half mv squared is. That's how much energy you'll have. Well, let's calculate it. A half, what's the mass of this kid? 60 times 8, don't forget the squared. We have 1,920 joules of energy. We have 1,900 total joules of energy to play with. As I go up the hill, I gain potential, I lose kinetic. But this number here will always be 1,920 joules. See if we can figure out the rest. Okay, so number 1 is good. ME is mechanical energy, and it's the total potential plus kinetic right there. Okay? I stole the picture from online, Antonio, but I liked the picture, and I thought it was good numbers. 2 is good. Good roller coaster. 3 is good. Good roller coaster. 4 is good. 5 is good. I think I'm going to give you all the homework. Yep, 6 is good and 7 is good. You have 20 minutes. I think you can get it all done in class if you hustle.